While learning linear models and the fitting of linear models to dataset, we have learned the 5 major assumptions made while fitting a linear model. One of the main assumptions is that there is no multicollinearity present among the predictors. By multicollinearity, we mean that the predictor variables are correlated to one another, and due to the presence of multicollinearity, there is faulty inference on the estimates of the regression parameters. Now, in order to make our data set free of multicollinearity, we need to use statistical techniques. In this module, we will discuss methods of detecting multicollinearity. When we have multicollinearity present, like I have mentioned before, there is faulty inference about the parameter estimates. So, in order to get our data rid of multicollinearity, we first need to detect it, and hence this module has been dedicated to the detection of multicollinearity from a data set. When studying linear model, the classical linear regression model is of utmost importance, and by classical linear regression model we mean the regression model where we have a dependent variable which we denote by y, and we have several independent variables which are denoted by x1, x2, xp, or in case of simple linear regression we have only one independent variable denoted by x. These are the conventional notations for a linear regression model. So, convention also tells us that there are certain model assumptions that we make when we want to use a linear model for fitting a data. What are these assumptions? The assumptions are the following. The relationship between the dependent variable and the predictor variable is linear. This is one of the most basic assumptions, and as the name of the models suggest that they are linear regression model, so the relationship between the dependent variable and independent variable being linear is a very common assumption. The next assumption is that the error terms are normally distributed. That is, the epsilon term in the model follows a normal distribution with mean 0 and variance sigma square. We also assume that there is no serial correlation between successive error terms. In other words, there is no serial correlation between epsilon I and epsilon I minus 1. The error terms have constant variance. This is the next assumption. When we say error terms have constant variance, we mean that in assumption 2, the sigma square that we had talked about, which is the variance of error term, that remains the same for every error term for every observation. This assumption is called the assumption of homoscedasticity. When the error terms have constant variance, they are called homoscedastic. When the variance varies from one error term to another, they are called heteroscedastic. And the last assumption is that the predictor variables are not correlated among themselves, and this implies there is no multicollinearity present. By multicollinearity we means a collinear relationship between the predictor variables. For instance, if we are studying a model where price of a commodity and income of individuals are the two predictors, there is a high chance that these two variables are correlated. In such cases, due to the presence of multicollinearity, including these two variables together in the model might end up giving us faulty estimates of the regression parameters. So, while trying to fit a linear model, we have to keep in mind these model assumptions, and any violation of any of these assumptions leads us to a number of statistical methods and techniques to detect the violation and to remedy the situation. So, when working with linear models, we wish that all the assumptions mentioned previously hold good. However, this is not the case always. Under certain situations, one or more of these assumptions are violated. For instance, when there is correlation between one or more predictor variables, we call it multicollinearity. Thus, the last assumption of linear model is violated. Again, when we have error terms that are correlated, when successive error terms are correlated, we say that autocorrelation is present. Again, there could be certain situation where the variance of the error term does not remain constant but changes with every observation. Thus, variance of epsilon I is different from variance of epsilon I minus 1. When this happens, we say there is heteroscedasticity present in the data set. So, in this module, we will look at the different ways of detecting multicollinearity. Like I have mentioned before, if there is a violation of any one of the assumptions of linear model, we need to make sure that we detect the source of the violation of assumption and remedy the situation depending on the type of violation present in the data set. So, when multicollinearity is present, we can use several different methods to detect multicollinearity and then look at several different methods, statistical methods, to remedy the situation. So, here is a list of the methods of detection of multicollinearity that we will be looking at in this module. They are high R square but few significant T ratios when we fit a linear model to a multicollinear data, high pairwise correlations among the regressors or predictors, fitting of auxiliary regression equations to the predictor variables, studying the eigenvalues and the condition index, and computing tolerance and variance inflation factor and looking at the rule of thumb cutoffs for these conditions to detect multicollinearity. So, let us look at the first method of detection, which is high R square but few significant T ratios. The most classical symptom of multicollinearity is that the value of R square is very high when we fit a linear model to a data set which is multicollinear. When we perform the overall goodness of fit test, the F statistic in most cases rejects the null hypothesis that the model is not significant. That is, the predictors are not significant all at the same time. But when we investigate the individual T statistics, when we try to test the individual regression coefficients in a multiple regression model, they show that none or very few of the predictors are statistically different from 0. When we notice such discrepancy in the inference, we can assume that multicollinearity is present. Now, a different method of detecting multicollinearity and a very crude method of detecting multicollinearity is by looking at the pairwise correlation among regressors. As we have learned in the module on simple linear regression, correlation coefficient is a measure of the strength and direction of linear relationship between two variables. Suppose we have two variables x and y, and we have reasons to believe that they are correlated. Then if we want to quantify the strength of the relationship, we compute the correlation coefficient between the two variables. So, in presence of multicollinearity, we know that the predictors are correlated to one another. So, a very crude method would be to take every possible pairs of predictors and compute their corresponding correlation coefficient. So, correlation coefficient, which ranges between -1 and 1, will give us a value of the correlation coefficient, will tell us what kind of relationship lies in between the two selected predictors. So, if we have a correlation coefficient very close to +1, then we say that a positive correlation lies between the two variables. If they are close to 0, then we can discard the idea of multicollinearity, because close to 0 means there is no correlation, and if it is very close to -1, then there is a strong negative relationship between the two variables. So, computing all possible correlation coefficients for all possible pairs of predictors in a regression model could be one way of detecting the source of multicollinearity. But there is a major problem with this method of detecting multicollinearity. Although a high pairwise correlation is sufficient to suggest multicollinearity, it is not a necessary condition. What I mean by that is that when there is high correlation coefficient between two variables, we know that these two predictors are correlated. However, if we compute the correlation coefficient and it turns out to be not so high, it does not necessarily indicate that for sure there is no multicollinearity present in the data set. So let us look at a model to demonstrate this fact. So suppose we have the following model with 4 predictor variables. Our response is yi, and the 4 predictor variables are x1, x2, x3 and x4. And we have written the multiple linear regression model in terms of the 4 predictor variables. And suppose that the 4th predictor variable x4 is perfectly linearly related to x2 and x3 in the following form. We have x4 equals lambda 2 x2 plus lambda 3 x3, where lambda 2 and lambda 3 are non-zero constants. So the linear equation in the previous slide shows that x4 has an exact linear relationship between x2 and x3. Now the coefficient of determination, which is denoted by r square 4.23 equals 1 in the regression of x4 on x2 and x3. Let me tell you here, when we had looked at the relationship between x4 and x2, x3 here, this can be thought of as a regression equation where we are regressing the dependent variable x4 on the 2 independent variables x2 and x3. So from this regression equation, if we obtain the coefficient of determination, we will write it as r square 4.23, where the subscript means 4 is the subscript for x, which is the dependent, and it is depending on x2 and x3. Now if this takes the value 1 in the regression of x4 on x2 and x3, now we write the formula for r square 4.23, which takes the form lowercase r 4.2 square plus lowercase r 4.3 square minus 2 r 4.2 r 4.3 r 2.3 divided by 1 minus r 2.3 square. Now in this expression on the right hand side we had coefficient of determination r square 4.23. If this term takes the value 1, then we can write 1 equals the expression for r square 4.2.3 in terms of the correlation coefficient. So the above equation in terms of the pairwise correlation coefficient can be satisfied for the values r42 equals 0.5, r43 equals 0.5 and r23 equals negative 0.5. I have not done the detailed calculation here, but I leave it for the students to compute and see that the above expression holds good. Now these values of pairwise correlation which we have used to satisfy the above expression are not very high values. However, when we plug these values into the above expression, that gives us r square 4.23 equals 1. So thus we have more than, when we have more than 2 predictors, then simple correlation coefficient is not always the best method of detecting multicollinearity. In other words, it is not the necessary condition for the presence of multicollinearity, although it is sufficient to indicate that multicollinearity is present. Now let us look at the next method, which is slightly more complicated than the previous crude method of detecting multicollinearity. This method is called auxiliary correlations. What we do in this method is fit auxiliary regression equations. So multicollinearity arises when one or more predictor variable is exact or approximately linear combination of the other predictors. In order to detect exactly the predictors that are correlated, we can regress each of the predictors on the remaining predictors and compare the corresponding r square for each of the model. So suppose we have 4 predictor variables, we take one of them at a time and regress them on the remaining predictors, and for each of these fitted models we obtain the r square. So suppose it is the ith predictor that we have taken and regressed it on the remaining predictor variables, then the corresponding r square obtained is denoted by ri square. So each one of these regression is called auxiliary regression, and hence the name of this method. So we have seen earlier in the module on Introduction to Multiple Linear Regression Model that there is a relationship between the F statistic that we use to test for the overall goodness of fit of a model and the coefficient of determination r square. Using that relationship, we can write ri square or ri in terms of r square. So the expression would look like Ri equals R square x1 given x2, x3, xp divided by p minus 2 divided by 1 minus R square x1 given x2, x3, xp divided by n minus p minus 1, where R square x1 given x2, x3, xp is the R square from the regression model where we have regressed x1 on the rest of the predictor variables. So in the expression for Ri, the statistic has an F distribution with degrees of freedom p minus 2 for the numerator and n minus p minus 1 for the denominator, where n is the number of observation and p is the number of parameters used in the fitted model. So as a decision rule, we check whether the computed F exceeds the Fi at the selected level of significance. So in other words, we compute F from the overall fitted model and we compute Fi for each of the auxiliary regressions, and we check whether the computed F exceeds the Fi at a selected level of significance, and if it does, then we say that multicollinearity is present, and for the ith auxiliary equation where we have xi regressed on the rest of the parameters, this is the source of multicollinearity among the predictor variables. So the rule of thumb that we use for this method of detection, so as mentioned in the previous slides, one way to find out which xi is correlated with the rest of the predictor is by fitting auxiliary regression and checking their Fi's or F statistics and the correlation coefficient of determination Ri square. However, instead of checking the Ri squares every time after fitting an auxiliary regression, we might adopt Klein's rule of thumb, which suggests that there is a chance of multicollinearity if the Ri square obtained from the auxiliary regression is greater than the overall R square, that which we had obtained from the regression of y on all the predictors. So let us look at the next method of detection of multicollinearity. This method is the use of eigenvalue and condition index. The use of eigenvalues and condition number or condition index to detect multicollinearity is also very popular statistical practice. Although we will not spend time in this module learning about the details of eigenvalue and their computation of eigenvalue for a given matrix, we will simply look at their use to detect multicollinearity. So when we are given the eigenvalues, the condition number is given by k equals maximum eigenvalue divided by minimum eigenvalue. So the first step in using eigenvalues and condition number and condition index is to obtain this ratio of maximum and minimum eigenvalue. Then our condition index will be given by square root of this ratio, which is square root of maximum eigen divided by minimum eigenvalue. And for this method as well, we have a rule of thumb. If the condition number k is between 100 and 1000, there is a strong to moderate chance of multicollinearity present. However, if k exceeds 1000, then there is severe multicollinearity in the data. Alternatively, we can also compute condition index, which is the square root of condition number, and detect multicollinearity. So if condition index is greater than approximately 30, which is approximately square root of 1000, then there is high multicollinearity. And finally, we can use tolerance and variance inflation factor to detect multicollinearity. Suppose we have a regression model where there are p minus 1 regressors and an intercept, which means a total of p regression coefficients. Then the variance of the jth partial regression coefficient, which is given by beta j, will be given by variance of beta j equals sigma square divided by summation xj square times 1 divided by 1 minus rj square, which can be written in terms of the variance inflation factor. Now we know from the definition 1 divided by 1 minus rj square is the jth variance inflation factor. So variance of beta j can be written as sigma square divided by summation xj square times variance inflation factor subscript j. So beta j here is the partial regression coefficient of the regressor xj. Rj square is the R square in the auxiliary regression of xj on the remaining t minus 2 predictors. And the rule of thumb for using variance inflation factor as a detection method is that higher the variance inflation factor, more certain we are that multicollinearity is present. But when I say high, I have to give you a threshold value beyond which if VIF reaches, then we say that multicollinearity is present. So we can use as a rule of thumb, VIF greater than 10 suggests highly multicollinear predictor variables. Also, tolerance, which is given by 1 divided by VIF, we can use the highest possible value of admissible VIF and decide on a cutoff for tolerance. When multicollinearity is present in a data set, it becomes important to detect multicollinearity so that we can look at the source of multicollinearity and remove it from the data set so that we can fit a linear model to the data. In this model, we have discussed several methods of detecting multicollinearity, and some of them were fitting an auxiliary regression model to our predictor variables, or using the eigenvalues and the condition index based on the predictor variables that we have, and we have also learned how to calculate tolerance and variance inflation factor, which helps us detect multicollinearity in a data set.